The last section of the chapter has to do with rational functions, which we've already touched upon in the past. We're going to take a little closer look at other rational functions. So let's go ahead and start with this example. Graph the line y equals x minus 2. Well, we know that that means you have a y-intercept at -2 and you have a slope of 1 over 1. So that's a linear function with a polynomial that's continuous everywhere. Okay, so why is it continuous? Well, because I can trace my finger, I can trace it with my finger forever. Both, from left to right, you read it from left to right, and I never have to pick up my finger. So that's a continuous function. All polynomials are continuous. Okay? But this here is not a polynomial. That's a rational function. Okay? So what do you notice in this? Well, these factors cancel, don't they? So if we graph y equals x minus 2, because that's what's left over, right? Shouldn't we get the same equation? Well, yes and no. The problem is that this rational equation is not the same as this linear equation. In this one, we have a restriction on our denominator. Basically, it's reduced to y equals x minus 2, but x cannot equal a -3. So this here is the same as this. Over here we didn't have that restriction, but on this one we do, because we reduced it and we can't divide by 0. So what would that look like? Well, let's go to -3. Over to -3. What would -3 be? If I plugged a -3 into here, it should be -5. So 1, 2, 3, 4, 5. Yep, -3, -5. Well, x cannot equal -3 on this one. So that means that we have what's called a hole in the graph. The function is undefined at x equals -3. Now you still have the same y-intercept, you still have the same slope, but you have a hole in your graph. Anytime there's a common factor in the numerator and the denominator, you have a hole at, in this case, -3. Plug it into the reduced equation, and that will give you the y value. The hole is at -3, -5. Now, if I trace this one, I have to pick up my finger to continue tracing. So this is discontinuous. This graph is discontinuous. Okay, this is called point discontinuity. Now there's other types of discontinuities. One is jump discontinuity and the other is infinite discontinuity. So we talk about this in calculus when we do limits. And again, the unit 1. Different types of discontinuity: point, jump, and infinite. Okay, so let's go ahead and let's take a look at this graph right here. We know x cannot equal -2. Let's reduce this. Now we could do long division and synthetic division if you wanted to, but I would always try to factor first, because that would save us a lot of time. So if a factor cancels, you can have multiple factors cancel. You will have multiple holes in the graph. So we have, what's left over is f of x equals x minus 2. Okay, but you have a hole at -2. So -2, -4, -2, -4. There's a hole in the graph. So So what's left over, let me make sure you understand, it's y equals x minus 2, and x cannot equal negative 2. That's what's equivalent to this. So we still have our line, but this time we have point discontinuity at negative 2, negative 4. There's a hole. All right, let's look at this piecewise function here. Okay, graphing piecewise, remember that? All right, so let's plug in a 1 here. Our starting point here is plug in a 1, you get 2. So 1, 2 is on the graph. That's 1, 2. We have a slope of 1, up 1 over 1, and we're going greater than 1. All right, so that's that piece right there. Now let's do this piece. 1, when you plug in 1, you get negative 1. But it's not equal there, so it's going to be an open circle at 1, negative 1. And we can use our slope of 2. And we can go up 2 over 2, but we have to go in that direction. So we're going to go down 2 over 2. I'm sorry, down 2 over 1. Sorry, down 2 over 1. Down 2 over 1. So there's that piecewise function. And one doesn't start where the other one leaves off. So if I'm going to trace it, again, left to right, I have to jump to the next piece. That's jump discontinuity. Okay, and now let's look at this one. This is a rational function, and again, on this one, x cannot equal 0. So in this particular one, we have a vertical asymptote at x equals 0. X equals 0 is a vertical asymptote. Now, if you plug in, you can't divide by 0, so this will never equal 0. So it just so happens that y equals 0 is also a horizontal asymptote. This is never going to equal 0. Well, what is it going to equal? If I plug positive x's in here, what's the fraction going to be? Positive. If I plug negative x's into here, what's the fraction going to be? Positive. Okay, so a sketch of this type of graph. There's a sketch. You can plot some points, but that's what it basically looks like. This right here is called infinite discontinuity. Basically, if you have a vertical asymptote, you have infinite discontinuity. Okay? All right, so let's take a look at this one right here. Again, I can divide or I can try to factor. I'm going to try to factor. So that's going to be what? X plus 3 times x plus 1 divided by x plus 3. Okay. So the reduced equation, so basically what this is equal to here, I'm going to write it down here so I'm running out of room. Basically what I have is I have x plus 1, but x cannot equal a negative 3. That's what this is. The graph of x plus 1, but x cannot equal a negative 3. Okay? So negative, if I were to include negative 3, that would be negative 3, negative 2. Negative 3, negative 2. But since I can't, I'm going to have a hole there. I have a slope of 1. Right, I have a y-intercept of 1. So there's another point discontinuity. Okay. Now I don't know if you remember piecewise functions. I'm sorry, step functions. They kind of look like this. Those are step functions. Those are also, that's also jump discontinuity. Okay. And let's take a look at this one now. Again, let's factor this. X plus 3, factor this. Hopefully you're getting better at factoring. X minus 5 times x minus 2, or x minus 2 times x minus 5. Okay, so you cannot divide by 0. Notice these don't cancel. Nothing cancels here. So it's this equation, and x cannot equal what? 2 and 5. But they're not wholes. They're only wholes when you can reduce the equation, but I can't reduce the equation. So they're not wholes. They are vertical asymptotes. You have to remember that. So at x equals 2, we're going to have a vertical asymptote. And at x equals 5, you're going to have a vertical asymptote. Okay. All right. So what else can we find? How about let's plug in 0 for x? Plug in 0 for x. If I plug 0 into here, I get 3 over 10. So when x is equal to 0, my y-intercept is 3 over 10. Okay. How about if my y was equal to 0? If my y was equal to 0, what would make this? Wouldn't it be your numerator equal to 0? Because wouldn't you multiply through by this denominator? So that would give me -3. So I know that that is a point on the graph. Okay, now if you plug this into your calculator, it's probably going to look kind of weird. But you know it goes through these 2 points here. Okay? So you know this is an asymptote. So what's going to happen is it's going to go through those 2 points. Okay? It's going to approach that. This right here, and again, you can get this off the sketch off the graphing calculator. That's going to do that. And then over here, it's going to do this. But again, if you don't know that there's vertical asymptotes, this is going to be really crazy looking on your calculator. So you can go ahead and try it, but you need to be able to understand this and interpret what your graphic calculator is trying to tell you. So anything that makes your denominator equal to 0 that cannot be reduced, that cannot be canceled, is going to be a vertical asymptote. Okay? All right. Let's see what we have next. Take a look at example number 1. Determine the places of discontinuity of the function. Okay, rational function cannot be reduced. Your denominator cannot equal 0, so x cannot equal 4. Now, is that going to be a whole, or is that going to be a vertical asymptote? Well, it's going to be a vertical asymptote, because again, I didn't cancel anything. All right, how about this one? Go ahead and factor numerator and denominator. Pause the video, practice your factoring. All right, welcome back. X plus 1, x minus 1, a difference of squares. X plus 2, x plus 1. Now, what do we notice? The x plus 1s cancel. Okay. The x plus 1s cancel. So what are you left with? You are left with a rational function, x minus 1 over x plus 2, and x cannot equal, well, -1, and it cannot equal a -2. So it's either a whole or a vertical asymptote. You can have as many wholes and as many vertical asymptotes as the graph has. So which one is which? Well, the one we canceled, that produces a whole, and any denominator that's left produces a vertical asymptote. Okay, so you have a whole at -1 and a vertical asymptote at -2. The question is can you come up with a y value for the whole? Well, if I plug -1 into this equation, or if I plug -1 into this equation, you're going to get the same answer. Actually, I lied. Here, you're going to get 0 divided by 0. That's why it's a whole. It's undefined. So plug it into the reduced equation, you're going to get a -2 divided by 1. So the whole actually is at -1, -2. That's where the whole occurs. The x value that's undefined is -1. Okay, next factor, again, a difference of squares. X plus 1, x minus 1, all over x minus 1. Okay, this cancels. So that means that you have y equals x plus 1, and x cannot equal 1. Okay, so 1, 2. X equals 1, y equals 2. X equals 1, y equals 2 is undefined. So we place a hole there, which means the function does not exist there. It exists everywhere else, though. So there is point discontinuity. Okay? Moving on. This is basically what we went over. Okay? We went over if f of x over g of x to be a rational function, f of x is a polynomial of degree n, and g of x is a polynomial of degree m, then the following asymptotes rules apply. We went over this one already. Okay, the vertical asymptotes. Now, this is new. Horizontal and slant asymptotes. Horizontal and slant. Now, if your n is less than your m, well, what does that mean? Where is the n? The n is on the top and the m is on the bottom. So let's just use an example. Okay, if it is 3x, we want the degree of the numerator to be less than the degree of the denominator. Let's say that we have a polynomial, and we'll need to look at the leading terms. This denominator is going to get a lot bigger than this one here. Did I do that right, or did I do it wrong, backwards? F of x is a degree of n. Yeah, that's right. Anytime this is larger, think about it. If you're going to infinity, if I'm plugging large numbers, the denominator is going to get larger faster. So if you divide by a really large number, let's just say anything divided by an extremely large number is going to approach 0. So you have a horizontal asymptote at y equals 0. Horizontal asymptote at y equals 0. Okay, so let's go back to this one, because people are going to have a hard time with this. Okay, you're like, well, wait, back at this one, you passed the horizontal asymptote, and I thought you weren't allowed to go through asymptotes. Well, your teachers lied to you. You can't cross vertical asymptotes, but what you need to know is horizontal asymptotes describe n behavior. So you can cross a horizontal asymptote here, but down here at infinity, negative infinity, positive infinity, at the ends of the graph, it's end behavior. So you can cross a horizontal asymptote, so don't freak out about that. However, the end behavior of the graph will approach y equals 0. Now, what if it was the other way around? Y equals 4x cubed on the top, and again, some polynomial, and the leading coefficient of the bottom polynomial was 3x squared. Okay, you're not going to have a horizontal asymptote when this degree is larger. Okay, now we could do long division and we could get a slant asymptote. You'll get a slant asymptote when this is 1 degree larger than this one. Okay, so slant or oblique asymptote they're called. That's right here. The equation of the slant asymptote can be found by dividing and then rewriting the function. So we can use our long division. Okay, so divide and you get your slant asymptote, which is probably new to you, something you've never heard before. Again, this is only 1 degree larger. You have a slant asymptote. So let's go to that one. So if we have, say, 4x to the n plus 1, and the bottom is x to the n. If this degree is 1 larger than this one, you'd have a slant asymptote. If it was 2 degrees larger, you'd have a quadratic asymptote, which we're not going to get into, so you don't have to worry about that. Okay? Now, what happens? This is when the top is smaller. This is when the bottom is smaller. What happens when they're the same? What happens when they're the same? So let's squeeze this in here. Y equals 4x cubed plus blah, 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 divided by 3x cubed plus whatever. It doesn't really matter. We're only looking at the leading terms. Make sure they're in order. So when the degrees are the same, that is your C that they're talking about. Your horizontal asymptote for this one would be y equals 4/3. So that's what you have to memorize. All the different possibilities. The top being larger, the bottom being larger always has an asymptote at y equals 0. The top being larger by 1, you'll have a slant asymptote. When the degrees are the same, you have a horizontal asymptote at whatever the coefficients are. Okay? So let's see what the big warning is here. A horizontal or slant asymptote has no effect on the graph except at the right and left extremes, which is what I was talking about, the end behavior. In particular, it is not true that a graph can never cross its horizontal or slant asymptote, again, which I already said. The graph might cross its horizontal or slant asymptotes many times towards the, quote, middle of the graph. Only when the graph makes its final approach to the asymptote at the left and right extremes, again, end behavior, will it squeeze up against the asymptote without ever touching it. Okay, by the way, it is true that the graph can never touch one of its vertical asymptotes. Okay, so I already stated that, and there it is in writing. All right, so procedures for graphing rational functions. There they are, nice and organized. Find the zeros of the denominator. Use those to help with the vertical asymptotes or any holes. Use the procedures given earlier to find and draw horizontal and slant asymptotes, which we just talked about. Find the zeros of the numerator. If you find the zeros of the numerator, those are the x-intercepts. Okay? Decide what the graph looks like near the vertical asymptotes and appropriately draw short pieces of the graph as it approaches from the left and the right. Decide what the graph looks like near the horizontal and slant asymptotes, if there is one. If the graph has no horizontal or slant asymptotes, determine what happens to the graph at the far left and far right extremes. You can substitute in very large positive numbers or very large negative numbers. Large negative numbers like negative 1,000. What's going to happen? Okay? Then you connect it all together with a nice smooth curve. So again, graphing without a graphing calculator, understanding how things behave. Okay, so let's take a look here. Okay, doesn't factor, doesn't reduce. So we know that x cannot equal a -1, must be a what? Vertical asymptote. Okay, so that's the vertical asymptote. Now what about a horizontal asymptote? This is degree 1, this is degree 1. Is there a horizontal asymptote? Yes, the horizontal asymptote, when the degrees are the same, we look at these leading numbers, which is 4/1. So you have a horizontal asymptote, horizontal, y equals 4. All right, so let's go ahead and put those in. Okay, we have a vertical asymptote, and again, a vertical asymptote is just a guide at x equals -1. X equals -1. Oh, I'm running out of black ink. All right, horizontal asymptote at y equals 4. And again, this is just a guide. This is telling you that the graph is never going to get to that spot. Okay, the function is undefined at all y equals 4 and all of x equals -1. Okay, bad pen. Okay, what else? Okay, you'll have a horizontal asymptote or a slant asymptote. If you have them, you can only have one. You can have many vertical asymptotes as you want, but if there's a horizontal, there's only one. If there's a slant, there's only one. And if there's a slant, there can't be a horizontal, and if there's a horizontal, there can't be a slant. Okay? Hope you got all that. All right, let's find the x and y intercepts. Let's plug in 0 for x. 0 for x, you get 3. Okay, so x-intercept, I'm sorry, that's the y-intercept. The y-intercept, 0 for x, and you get 3. How about the x-intercept? Now, the x-intercept is plugging 0 in for y. And again, that's the same thing as setting your numerator equal to 0, because multiplying through will cancel this out. So 4x plus 3 equaling 0, 4x plus 3 equaling 0 gives you a -3 over 4 comma 0. So there's your x and your y intercepts. So let's go ahead and plot those. -3/4, 0, 0, 3. Now, see these asymptotes right here? Okay. You don't normally cross the horizontal, but it is possible. So I'm going to guesstimate that this is gonna do this. Okay, and that is true. You can plug in a really large positive number into here, and it's never going to get up to 4. Okay, now these are all functions, right? So they're all going to pass the vertical line test. There can't be anything up here. And again, if there's a branch over here, there's going to be a branch over here. Okay, again, just like our other rational functions. So there's a sketch. You want to plot another point here? You can plug another point in. I think if you plug in a -2, I think you get 5. So I think I might have missed the mark there. Yeah, plug in some points. Oh, it's getting late, people. It's getting late. Okay, so plot some more points. Make a table if you want to. X, Y, I plugged in a -2, and I end up getting 5. I don't know, plug in whatever you want. Get some more points. Okay, all right, let's try the next one. Okay, always factor first. X minus 2 over x minus 1. Okay, so no holes. Denominator gives us a vertical asymptote at x equals 1. Okay, horizontal asymptote. Horizontal asymptote. Yes or no? No, no horizontal asymptote. How about a slant asymptote? Yes, slant asymptote. So I'm going to do long division. X minus 1. I could do synthetic. Let's do synthetic division. We're dividing by x minus 1, so why don't we do synthetic? So 1 is my a value, and I have 1x squared, a -2x, and 0 is my constant. So 1 times 1, -1 times -1. Is what? -1 times is -1, so a remainder of -1. So my slant asymptote is this right here. My slant asymptote is y equals 1x minus 1. Now what happened to the remainder? That's your slant asymptote. Now, watch this though. -1 over our divisor, x minus 1. What do slant asymptotes describe? They describe end behavior as x gets extremely large. So let's say this is a really large number. 1 divided by a really large number, positive infinity. You can't really evaluate positive infinity, but the idea of 1 divided by a really large number, because we're talking about the end behavior here, or a really small number, I mean, a large negative number, this is going to become 0. That's a limit. That's going to become 0. So this right here is your slant asymptote. That's the equation of your slant asymptote. Okay? So you can drop off the remainder because this becomes pretty much absolutely nothing at the ends. Okay? So let's go ahead and put those in. Vertical asymptote at x equals 1. You have a slant asymptote at, so let's see, we go through -1, slope of 1. See if I can get a straight line here. I probably should pull out my ruler. I know I'm going to mess up. Oh, we still will mess up. So 1, 1, 1, 1, 1, 1. I don't want to miss anything. All right, there we go. So again, there are your guides for your graph, and something's going to happen with those, okay? So those are our asymptotes. Now let's do x-intercepts or y-intercepts. You want to do x-intercepts first? Okay, so the x-intercepts, okay, those come from your numerator. So this is equal to 0, so we have 0, 0 as an x-intercept, and 2 is also an x-intercept. So we have 0, 0, and we have 2, 0. Okay, now you're not going to cross the vertical asymptote, so this is a point on the graph. These are guides of the graph. All right, how about the y-intercept? Plug 0 into here or into here. Doesn't really matter. When you plug 0 in for x, you get 0 for y. Okay? So again, x-intercepts come from the factors of the numerator. You remember that from Algebra 1. Okay, so obviously 0, 0, 0, 0. Okay, so that's all we know. So what's going to happen? Let's see. I don't know. Let's plug in some points. Let's plug in some points over here. I don't know. Let's say I plug in a 5. If I plug in 5 here, I get 5 times 3, which is 15 divided by 4. I get 15 divided by 4. Okay. Well, if I plug 5 into here, I get 4. So this is 5, 4. This is less than 4, right? Just a little bit less than 4. So it's going to get really close up here. Okay, so it's getting close there. So it's never going to cross this. It's going to get close to this. It goes through this. So again, a nice smooth curve. Oops, I probably should do a different color for the graph. And again, it doesn't curve back in. It approaches the asymptote. Okay? So there's one piece. All right, now what about the other one? What happens? Well, I know it goes through this point. So let's pick a point over here. I don't know, let's pick -1. Let's pick an x value. Plug in a -1. Again, into this one, it doesn't make a difference. So carefully, -1 squared is a +1, plus 2, that's 3, divided by -2. So that's 3 divided by -2, so it's about -1.1. -1.1. So I bet you if I plug in larger numbers, it's going to keep getting closer to this. And again, you can't cross the vertical asymptote. So we're going to try to make a nice smooth curve here. Okay. All right. So those branches, these two branches are the graph. The other dotted lines, which I probably should have put in a different color, are the guides of the graph. They're not actually on the graph. All of these points on this branch and all of these points on this branch are the actual graph. So something a little bit different than what you're used to. All right, so let's take a look at the next one. This right here, let's talk about, okay, always factor first. So I hope that bottom factors. Multiples of -5 that total +4. Yep, I can do that. That's +5 and -1. All right, nothing cancels. There's no holes. We have 2 factors left over, so we have 2 vertical asymptotes. Where are they? -5 and 1. Okay, how about a horizontal asymptote? Remember this one? Bottom is larger. Horizontal asymptote is y equals 0. Again, that's the memorize on the previous page. So if there's a horizontal asymptote, there can't be a slant. Okay, let's go to x-intercepts. X-intercepts. X-intercepts come from the numerator set equal to 0. So that's 0, -3. Oops, I got that backwards. -3, 0. Not 0, -3. -3, 0. Y-intercepts, so when you plug 0 in for x, again, into this one or into this one, it doesn't matter. You get a -3/5. Okay, so that's enough to get started. All right, I'm going to, let's use red as our guide here. So we have a vertical asymptote at -5. Okay, x equals -5. We have a vertical asymptote at x equals 1. Okay, we have a horizontal asymptote at y equals 0. Okay, so those are our guides. All right, so what are the points that we know here? We know -3, 0. Okay, we know 0. And -3/5. So it's going to be right about there. All right, that's about all we know. So what's going to happen here? Well, I don't know. Let's make a table. Let's plot some points to see what happens. All right. Well, if I know that it's going to go through here and it's going to go through here, and I have vertical asymptotes, I know it has to approach those vertical asymptotes, and it has to go through those 2 points. So I know that this is a sketch. It has to look something, whoops, yeah, maybe I took the curve a little bit too tight there. I'm not tight enough. Okay. So again, I don't want you to think that this is curving back in. It never gets there and it never curves back in, okay? So I know that that's going to have to happen. But what happens on the other side? So let's pick something over here. I don't know, let's pick 2. Plug 2 in for x, you get 5 4, 8 minus 5, that's what, 7? 5/7. So 2 and 5/7. That's going to be right about here. What if I plugged in a really, this is a horizontal asymptote, right? So I know it goes through this. I know it has to approach the vertical asymptote. And I know that it's going to, the end behavior is going to approach this. So I can plug in some more points, but I don't think I need to. Use a pencil if it helps, or erasable pen. Again, try not to touch the asymptotes. They're not going to touch, and they're not going to curve. It's not going to curve back in, okay? Now, what about over here on this side of this vertical asymptote? Oh, let's plug in, I don't know, -6. -6. -3 on the top. That'd be 36 minus 24 minus 5, right? So that's going to give me a -3/7, somewhere around there. Okay, so I know that it's going to be down here. This point's down here, and it approaches these, so again, try to make them look as smooth as possible. So there's a sketch. All right, one more. Again, let's start by factoring. Yeah, that factor. So we've got 3x and 1x, guess and check. One's going to be a positive, one's going to be a negative. I want the larger one to be positive. All right, let's try this. So my outside is -3x. My inside's positive 5x. So yeah, that's right. And the bottom is x plus 2 times x minus 2. All right, nothing cancels, so there's no holes. You can have holes and you can have vertical asymptotes, but they haven't given us any holes. Right now, they're just vertical asymptotes. So we have a vertical asymptote. We have 2 of them at x equals 2 and -2. Let's go ahead and put those in while we're at it. Okay, how about a horizontal asymptote? What do you think? Do you remember that? Same degree, horizontal asymptote, y equals the leading coefficients, 3/1. Y equals 3. Let's go ahead and put that in. 1, 2, 3. Y equals 3. All right. So the horizontal asymptote, there's no slant asymptote. All right. X-intercepts. Do those next. X-intercepts come from the numerator. Set this factor equal to 0. You get -5/3. Set this one equal to 0. You get 1. So there's your 2 x-intercepts. Again, we're just estimating -5/3. That's almost a -2. Not quite. Right here. And then 1, 0 right there. Right. Y-intercept, plug in 0 for x. Again, doesn't matter which equation. -5 over -4, you get 5/4. So 1 1/4. 0, a little bit more than 1. Okay, so that kind of helps us out with the middle piece. Okay, we know that we have to go through these points and approach these asymptotes. So carefully sketch the graph. All right, but now we have to check on each side of the asymptote. So let's just make a little table here. Let's check on this side. Let's just go right over here to the right. Let's plug in 3. Ugh, this isn't going to be fun. When you plug in 3, what do you get here? 9, 14 times 2 to get 28 on the top. And plug in 3, you get 5 on the bottom. So 28 fifths. So 5 goes into 28 a little bit more than 5 times. So 3, a little bit more than 5. It's going to be here. Okay. So we know that our branch is going to be up here, and it's going to be approaching this vertical asymptote. And as x gets bigger, it's going to be approaching this horizontal asymptote. All right, now let's check on this side of this vertical asymptote. So let's try -3. Okay, get something close here, right? 27 minus 6 minus 5. That's going to give us, if you plug it into here, 16 on the top and 5 on the bottom. Yeah, negative times negative, so positive 5 on the bottom. So that is a little bit more than 3. 5 goes into 16 a little bit more than 3 times. So we're just estimating -3, +3, a little bit more than 3. So right around there, we know that point. And again, it's approaching this vertical asymptote. And as x gets smaller, it is approaching this horizontal asymptote. And there's the sketch. And I'm going to sneeze. Okay. All right. Isn't that fun? Graphing rational functions. Memorize all of this stuff and all the different parts and pieces that you have to put on the graph without a graphing calculator.